Well, hello and welcome to today's show. As you can tell, I need a shave and a haircut. 2 bits. And today's my 2-bit take on some of this nonsense we're hearing dealing with ventilating a PC case. We hear a lot of people talking like they know what they're talking about. Oh, we're going to build a positive pressure. Your design, you need to figure out if you want a positive pressure design or negative pressure design. All of this nonsense. The truth is, unless you're having a fixed RPM DC type fans that don't change, you're really not designing for any one given point. And the relative pressure from inside to outside can change dramatically depending on how you have your fans kick on, if they're PWM, and where they're going, whether or not you have that variable speed that it can give you changes the dynamics, especially if you don't turn things off. Now, in the end of this show, if you stick around to the very end, I will tell you a surefire way to keep the dust from entering your computer. Now, that was another thing that I heard recently is I will tell you a surefire way to keep the dust from entering your computer. Now, that was another thing that I heard recently is it's all about, well, if you do this way, if you have positive pressure, the dust will be here, and negative. And the reality is dust goes just like a bug hitting a windshield. You know how you get the bugs on your windshield? Your car hit one. You know what happens when he misses you? You don't get the bugs on your windshield. Your filters in your home, your air filters, they clog up when a piece of dirt smashes into a dust. And if it doesn't do that, they'll eventually settle down from the top. If those that are heavier than air will settle down. So the only way that you're going to keep dust from really messing up your PC is to not run fans. Do you need to have as many fans, and do you need to have the volume in there? It all depends on your approach. Well, let's start with something right off of the beginning. I want to start, and I'm not picking that at Lee and Lee. I like Lee and Lee. The big system I'm building upstairs with the water loop waiting on Arrow Lake, that is a Lee and Lee case, although I didn't buy Lee and Lee fans. I'm looking at these. We're starting out at the Unis. I looked at Unis. They have different series. I like the ones with the LCD screen in it. Look over here, by the way. This is my mouse. Watch how far we go down when we go with this mouse. I like the idea of being able to use the screen as, GPU air temperature, water temperature, CPU temperature. But now we go through this. We're right up top. And we find out what they think is important. What's gearing itself to us is we have that they're easy to daisy chain. They should have like in my mind, a little zero around this to make like the Noble thing, or another X here to make an X. But the daisy chain, they're not hard to wire together. L connect, which is the interface, pretty well much goes with this, easy to connect. Multiple effects because they're ARGB. It also goes with L-Connect. High static pressure, quiet operation. Yeah, maybe premium quality sandblasted aluminum parts. I don't remember Lee and Lee's having aluminum parts, but that's okay. Unprecedented flexibility, quicker installation. Well, I do like the way they kind of snap together, and everybody's got a version of that. 16 of them will go on one controller. They make them in both black and white, and 120 and 140. Modularity. Now, as far as I know, you can't make the 140s to 120s modular together, but you could maybe daisy chain them together with the connectors there. But see, we're going way on down. We're seeing all of these neat features. There's some of their L-Connect software, and it tells you what they do. And we'll keep going down. There's the little module and the connectors and the fans, how to tell old from new, and the kits. And to me, you buy what you like, but to me it just seems like a lot of faff. It's just unnecessarily complicated to put all this ARGB kind of stuff in there. I don't mind the red ones like what came in my old machine. I've replaced them with red ones after that, but we'll talk about that. The new versus the old, and the mounting, and the 120s are bigger. And at the very, very bottom, we actually hit. See, this is where we are down here. let me move myself out of the way. I'm way down here at the bottom. The very last thing on the page is the actual specifications of the fan. Everything above this is like visual. They're pretty and they're easy to work with. Now, I don't mind the easy to work with, but look at this. Here they said they're high pressure fans. 2.54 millimeters of water. I don't know. Does that sound high to you? What do we have in it? Okay, well, the 40s are 1.67, so that makes the little ones, the 120s, look better. But let's look at them, because they are 120 and 140. But now, what else do we want to look at? Look at the airflow, though. It's 58, almost 59 to 70, right? So the little ones don't produce as much air as the big ones. What about the minimum speed? 800. That's going to give me a kind of a minimum level of quiet to 1900. But look at how much better the 140s are. They're 500 RPM. It's going to be a lot more quiet, I'm thinking, because it's turning a lot slower and it produces more air. Both have fluid dynamic bearings in the PWM, DC 6 volt. But look at the wattage of this, 5.16 watts per fan. And think about it. You could, it's not quite, 2 times 70 is 140, and these are 60 a piece, so 3 times 6 is going to be 180. So almost 2 of these can make what 3 of the 120s produce. So we know that they take quite a bit of watts, 3.6 on the 140. So you get better airflow, quieter operation, lower minimums RPM, and lower wattage if you go with the 140s. But what do we almost constantly go for? The 120s are the most common. They're easier to put in, and we end up buying more fans that way. Well, let's go back and look at so now let's look at the thermal takes that I replaced in my system. They were LED fans. You saw the blue one. There was one blue, one red. The blue one died. Okay, it died, so I replaced it. Pure A12. That's the small one. Pure A14's the big one. We'll look at their specifications and maybe go back to look at Lian Li just to see maybe Lian Li is significantly higher than other people's brands. I don't know. If we don't have a reference for what high pressure means, it sounds pretty good because we know 2.5 is bigger than 1 or bigger than 1.5, whatever we got. So, all right, look at this again. All right, this is the 120s, the 12 up here, 12 volt, 1.8 watts for one fan. Now, these do have color to them. You just can't change them. 1.8 watts for a 120 fan versus Lian Li's 5.16 watts. So it's going to cost you more if you do ARGB, because at least you know that those LEDs are going to take a lot more power supply to run them. Look at that, 56.45 CMN. The other one was, if you remember, was 58, but let's look at this noise level that the thermal takes have. 25.8, call it 26. What was it over here on the Lian Li's? 31. So the Lian Li's, more power, more noisy. They have a 800 minimum RPM. Do we have a minimum RPM here? Yes, look at this. The old thermal take, simple, cheaper, just one color fan, 500 RPM to a lower 1500 RPM. Up here, it was 1900, and it produces less air, or just slightly more air, but produces more noise. So I think we've probably spent enough time on that. The big ones of these we're going to refer to in a minute. They have 93.15 CFM for 33.24 watts. It's very efficient. So both of them have hydraulic bearing. Look like good product lines. Just one of them you can change and do the runaway lights and have all that extra wiring to put in and stuff, and have to have a bigger power supply and all that wonderful stuff. I'm not against having a little color in the case. When I redid this one, I use the thermal takes. I got a 120 in the back where the red Corsair fan was, and you know, I'm not against that, but it's just there's a point at which I start wondering if I'm being played, you know, being convinced that I like something or something's cool. All right, now let's look at this. This is from a place called Eldridge. If I put my thing up there, you see the little link at the bottom. You can look at that. It's a blog. Basically, we're going to talk about pressures for just a second. This curve is on inches of water column. IWC is a different way of saying WG, water gauge. 0 pressure to high pressure, 2 inches. You see on that side 0 to say 25,000 CFM for this blower. This is a system blower, and here's the system curve right here. We can let the system curve represent the pressure that we would build up statically and dynamically in our little computer box versus the ductwork in the system here. But what we do see is when pressure is 0 when pressure is 0, we have high flow rates right here. Right? When pressure is high, say at 1.8, we got no flow for most of these operating points, none at all. Some of these fan curves at different pitches, I think that's what these are, pitches of inclination. So when we have a lot of pressure, no flow. This is flow this way, pressure this way. High pressure, no flow. No pressure, high flow. So we get sort of a relationship like that. Now, we were talking about this, what's being marketed to us in terms of these vane axial fans, okay, as being high pressure. What does that really mean? And people talk about that. Well, if you're building up pressure in your case, like it matters. Like it flipping matters. For the most part. Where it would matter is if you build up pressure in your case, you're going to stop the fan. If you build up pressure in that case, your flow goes to squat. That's the important part of it. But the other stuff just becomes sort of nonsense. It really does. Now, looking at this NIH article that I have pulled up right here, National Institutes of Health, National Library of Medicine. Let me put my pretty face back on there. Let me slide this down. If I haven't lost it, it's under figure 3, under the NASA people. Let's go put some things in perspective. Normal breathing in contaminated air environments. All right. Now we're looking at this, but where I've got down here at the bottom are these numbers, because unless you look at this, you really don't know what high static pressure is. It certainly is not 3 millimeters of mercury or 3 millimeters of water. Now, it says, as such, normal breathing with typical respirators, these are mechanical lungs breathing for you, are about 4.5 to 6 millimeters of mercury pulmonary pressure, which is well below the upper limits. This is what I'm getting to, 40 millimeters of mercury. They're saying is the upper limit. So let's put these numbers in perspective. We saw that we were on that blower, that squirrel cage. Like if you have a high pressure system, what do you use to drive it? Sort of a centrifugal fan type thing. In your car, what runs your heater core? Lots of ductwork, squirrel cage. What's running your air conditioner inside of your house, running through ductwork, squirrel cage. What's outside on the condenser fan? Axial fan. Low pressure, just pulling through a coil. That's about it. But pushing through the ducts, pressure. So I'm having a problem with people abusing the word pressure. So what do you say we look at this one? What is 1.8 inches of water column in millimeters of water? 45.7, almost 46 millimeters of mercury. What did that Lian Li fan push? That high pressure, 2.54 millimeters of water is considered high pressure. Maybe for a vane axial fan, but not in terms of real life. And what can we breathe? What can the lungs put out? Well, if we can have this isn't still in water. Let's find one in terms of millimeters of mercury. Okay, here we have it. If 40 millimeters of mercury are the upper limit of the lungs, as we're seeing here from this NIH article, according to Bellamy and Lungu in 2016, then 40 millimeters of mercury is equal to about 21, a little less than 2 feet of water, which means if you had a 2-foot piece of pipe, you could blow into a pool and force air to bubble out. Would that be considered high pressure, considering the fact that we're looking at these fans that have only 1.59 millimeters of mercury, or of water rather, or 2.54 millimeters of water? And these are considered high pressure. So the simple reality, seeing the fan curve, you see that when you exceed that maximum pressure, the fan quits pumping air. In fact, there's a stage that we have in our fans that's called the stall phase, if I could spit it out. Blooper reel as we go. Main actual fans, they just don't move it. There really is no such thing as pressure. There's just maybe just a little bit more on the discharge side than the suction side. You know, a little more suck than a little more blow, but your lungs can create more air pressure than a computer fan. So what do you say we look at this high technology based experiment that I conducted for you? I probably will repeat a few things, but bear with it. There'll be something good in there for you to see, and at the end I'll tell you a surefire way to reduce the amount of dust inside of your computer, and then a serious one as well. If you'll forgive this game day decision, I'm going to just modify this, split this one video into 2 parts, put the test where I demonstrate the principles I'm telling you in a different video so that I can get to this. I want to talk about the dust collection on it and what the reality is versus what the monkey see, monkey say do is. So let's look at one more fan. Now, I don't know if you know this. There's no way that you would know this. I had my machine that runs a roaster upstairs. The hard drive died. It's dead. I have to cobble together a new machine. It doesn't really need much. I only use it for label printing, you know, for the shipping labels and product labels, as well as, you know, just running the roaster so I can see the curves. Well, the one I had died. So now, since I just gutted this old machine, and piece by piece, not intending to do just a full rebuild, else I just bought a case I like better than this one, I got all the old stuff that's perfect for doing that. And now I've got a new case coming, and I'll have to cool the new case, and I'm going to make it look much like the Lian 011 Evo XL. I'm just going to do this one. It's a smaller one. It ought to be a nice build. It's a difficult build because the size of the case is persnickety. You got to put the birthing person board in first. After you take the stuff for the power supply out, then put the power supply stuff back, and then go from there. Anyway, let's look at this one other fan. Okay, now this is an Arctic. It's a PWM version of the P12. All right, another 120 millimeter fan. They have 4 different versions. They got some semi-transparent blades and then some opaque blades in black and white. So 2 colors. Not got a lot of options there. You're not going to see fancy colors and lights. I don't mind the lights like in the ones I just showed you from Thermaltake that have been discontinued. I'm not against having a light in a case as long as it's not water cooled. It's not a good idea if you have water cooled. But if you don't have water cooled, it's not a bad deal, but there's something for dust collection we got to talk about, and we're going to see it in this fan. Now, first of all, this is only about a $10 fan, not a $30 or more fan, but here's all the stuff they want you to see. First, plenty of colored graphics to catch your attention. There it is. But here's the big part: 200 to 1800 RPM, regulated by PWM. It's got a fluid dynamic bearing in it, as I saw on the description. We come down here to the technical specifications. Okay, I've already opened them up. What does it say here? Airflow is 56, so they're just about parallel with the other, 120 millimeter fans. It's got pretty decent static pressure, 2.2 millimeters of water for this type of fan, which doesn't have pressures. It's 0.3 sound, which is pretty quiet. If you're not used to sound, it's just a way to refer to the noise it makes. But it will actually go 0 RPM below 5% PWM. Now, why would I want to do that? The simple thing is, just like when you get a bug splatter on a windshield. When did the bug splatter on your windshield? When it ran into your windshield. Okay, so when does your filter in your cabin filter in your car or in your house get dirty? When a piece of dust that's airborne flies through it and slams into that surface, it collects dust. So what can you do to lower the amount of dust your system builds up? Well, one thing you can do is cut the fans off if you can. Okay, now the video card in there has a 0 dB mode, which is a nice way to say we cut the fans off when they're not needed. And we have a 0 dB mode in our power supply. If I'm not mistaken, it has one too, and it will shut off if it doesn't need it. You can do the same thing with your PC. You could even technically do that with your cooler on your CPU if you have the ability to wake it on temperature rise. And so if you don't need cooling, turn the blessed fans off and don't put as many fans in there just for the sake of having colored lights and that kind of nonsense. Yes, you can run them at a little lower RPM for the same amount of airflow, but you're spending a lot of money for what? And some of those fans, going back, let's go to the Lian Li's. If you remember, their minimum speed is 800, so they're going to build up, we assume, if we have sort of a linear characteristics that we can extrapolate over the different fans, which we can't, but if we could, we would say that minimizes out at 800. The pure 120s from the red ones that I put in, they minimize out at 500, and this PWM version of the A12 of the Arctic, this $10 fan, will cut off at 200. So even if you can't turn it off, if your motherboard doesn't allow anything below a minimum, you're still going to have the least amount of air if you use this fan, and it's the cheapest. And if you don't like the lights, which I don't, you can love them all you want. You buy your fans, you build your own system. I'm trying to design an airflow system, not just simply have a high number of exchanges of airflow inside of the case. Does that make sense? Let's talk a little bit about the stall and the pressure that causes the stall. Now, regardless of the number of fans that you have, we can talk about just having one of each. Right now, one exit, one entering fan, and as long as they're matched, they're going to pull the air across your case and whatever's in your case. But what happens with a fan, a boxer type fan, is you see those gaps. If I can get my shirt in it. Hey, appreciate you watching. Do me a favor, if you will, subscribe to the channel, either the YouTube or the Rumble channel, which this appears in. And if you can, check the notification bell or settings to make sure that you get notified when new videos are posted. Appreciate it. But what happens with a fan, a boxer type fan, is you see those gaps. If I can get my shirt in it. At the given pressure that's the maximum it's rated for, or it's measured at, it can't push anymore. It just starts to circulate around the fan, the tips of the fan, the edges of the fan inside, and it just makes noise. It doesn't make any more air. Now, if we reach that flow, say this is a 50 CFM fan. If it was 50 CFM and we hit that pressure at 15 CFM, it's not going to put any more air through the case than 15 CFM. Because after 15 CFM, the pressure has hit that maximum and it just starts cavitating, for lack of a better word. If it was a propeller in the water, like a boat propeller, we'd call it cavitation. It's just going to short circuit around the blades in that assembly. And that's all it's going to do. Now, if the exiting fan is able to pull, say, 20 CFM, that's going to allow the pressure to drop to the point where the intake fan now pushes 20 CFM, and then it's going to cavitate. So putting a lot of fans in a system it can help, but it's not going to necessarily increase the airflow unless you increase the outflow in the same time. They need to match, because when either side gets its maximum pressure, each fan is going to start to cavitate, and they just make more noise. That's why a lot of these low-speed fans work a little bit better, because one, they don't make much noise. If you had them by themselves and plenty of room for it to breathe, they'd move a lot more air. But you close off that box and it's the pressure effect. The quote high pressure units are maybe cut a little bit closer, the geometry is a little bit different, whatever it takes, it can just go to a little bit more pressure before it cuts off. So if you have high pressure fans on your rads, you may be losing that in the flow across the radiator itself. And so that may be, it's going to do what it's going to do. It's going to pull as much as it can pull until that fan can't pull anymore. And then after that, the more you spin the blade, it just makes pretty much noise at that point. You don't really increase the airflow. Now, most of the new cases that I've seen, they're not really designed for airflow. What they're doing is they're taking a volumetric effect to it. We're not really flowing across like a motorcycle's fins, okay? It's not water cooled, so it's got to flow over a surface area. And the bigger the surface area, the more the surface area, the easier it is to get the heat off, which is why a high fin per inch count on a rad is more efficient, because the closer you get those fins, the more you have to get them. In fact, even here on this cooler, you see, flip it around that way so you see the number of fins. The closer the fins are, they do two things. You get them too close, they create too much pressure trying to flow across it, but you have the surface area, so that takes heat off. By having fewer fins per inch, you can get better airflow across, but you have less surface area. So we would typically want to see something like on a 1-inch rad, like on an AIO or something like that, just a mounted rad. We would look for a lot of fins per inch, because we don't have that thick of an obstruction. Rather, they're not causing as much pressure drop across the rad itself. But as we start to move that rad and make it thicker, we want the fins faced out a little bit wider, because we're going to compensate the cooling capacity by having more water. Yes, it becomes less efficient the thicker the radiator you have, or the thicker the cooler you have per fan blowing on it, because they really can't take very much pressure, but you have more water, and so you can build up more thermal capacity in the water that they hold. With your airflow, you can often get by with a lot less fans if you're using them in a balanced configuration. And it's so easy to get them out of whack when you're setting your fans in your motherboard, your berthing person board. You set those fan curves. You don't necessarily look at the percentages. You have to look at your guesstimate of what is your percentage on that given fan or number of fans. Now, in this box that I just built, because I have holes underneath the GPU and I have open area where it would be a 240 cooler could go, except with that case it can't, because it's just a poor design, poorly thought out case. and the board actually goes right up to the top of the case, and so there's no room for your wires that power like the 8+4 and the top connections. There's no room up there to do the bend radiuses and that kind of stuff, and still keep it out of the way of the rad that would have to fit in that space. So even though it's got the holes up there, the perforations up there, you can't mount one there with this case because it doesn't allow you to come off of the top enough to run all that stuff and still fit it in there. The width is okay, but the width in leaving that space between the wires is too small because the board is too high. But it does allow those two 140s, before they reach that cutoff or that cavitation, it lets them run a little bit more air through the top, and it runs a little bit round through the bottom. But at the end, if I'm overpowering how much I can vent from pushing into the case, it's just going to stop at whatever airflow those fans are, and then they just make a heck of a racket. So you can cool with a lot of fans if you keep them balanced, but what you're doing in most cases, you're just trying to change the air volume in terms of how much CFM is going in and coming out. You're trying to get as many exchanges of air, of volume, as possible within it, because once it hits that pressure, it's just going to go around the fan. It's just going to go around the fan and make racket and not push any more air. And you might do that with one fan at a certain percentage, or two fans at a lower percentage, or three fans at a lower percentage. And if you're interested in trying to keep the actual speed of the fan down, that might help to have three fans sharing the load at a very low RPM, if that makes sense. And again, it's about the balance in and out of it. It's really not about designing the airflow. You can't design airflow unless you design the fan speeds to go with it, if that makes sense.